So let's talk about another instance of an orthonormal basis that comes up quite frequently. So imagine our x is n by p, and let's still assume that p is less than or equal to n. But imagine if we have a large number of subjects or records, so n is large, and then p is also large. So we want some way to reduce the dimension of x to make it a little bit more manageable. Consider the singular value decomposition of x. So x is n by p of full column rank, so we can decompose it into u d v transpose, where u is n by p, d is a p by p diagonal matrix of singular values, and v transpose is a p by p matrix, and these are such that u transpose u equals v transpose v equals I. Okay, so one thing I want to know is imagine for the time being that x has been centered in the sense that all of its column means are 0. And consider x transpose x, which is effectively the variance-covariance matrix of the x matrix, disregarding the n minus 1. Well, that's equal to, using this result and this result, that's equal to v d u transpose u d v, which is equal to v d squared v transpose. So the eigenvalue decomposition of x transpose x is related to the singular value decomposition of x by itself. The squared singular values, the eigenvalues from the eigenvalue decomposition, help summarize the variance in the x transpose x matrix, which is itself a variance-covariance matrix. And these are usually ordered so that the larger d squared values are earlier. So they're usually ordered in decreasing decreasing numbers. So the first one is the largest, the second one is the second largest, and so on. And so consider the fact that the trace of x transpose x is equal to the trace of v d squared v transpose, and then I can move that v over there, since trace AB is trace BA, v transpose v is I, so the trace of x transpose x is equal to the sum of my eigenvalues squared. And so what this means is the eigenvalues are summarizing the variability in the sense that the trace is the total variability in my x transpose x matrix by taking all the diagonal, the sum of all the diagonals, sum of all the variances. Okay, so what we could do is say take the first 3 components of our decomposition and see what percentage of the total variation they explain. Let's suppose they explain 90% of the variation. Then we might consider reducing x by only taking those first 3 eigenvalues, first 3 eigenvectors. So consider the way to do this. Okay, notice that v transpose x, wrong direction, v times d inverse is equal to u. So a way to think about how we get at the scores, these are the so-called scores, the u, the vectors associated with u, is by multiplication of x by v. So what v does is it combines the columns of x in such a way that it gives us these scores, and then the d inverse is sort of a normalization term, right? The d's are you can think of as variances, so multiplication by d inverse is sort of like normalizing in the sense of dividing by a standard deviation. Okay, so what we could do if to every column of v, which is an eigenvector, is associated an eigenvalue, which is the element of d squared, we might take the top 3 and then only say take the first 3 elements of this U matrix. Okay, we might, so by only taking the first 3 elements of V and only taking the first 3 elements of D, or we could just of course do the singular value decomposition, which will give us U, D, and V, and just take the first 3 vectors of u. So we could then try to minimize y minus u gamma, let's say, squared, okay? Where I'm going to put a little 3 under my u because I just happen to grab the first three columns of u. And what this would mean is I'm trying to regress y with a design matrix u, but my u was selected in a way to capture as much variation as possible as I could in my x. Of course, I'm just using 3 as an example. You could use any number of the number of columns of u to do this with, but you want to explore what percentage of the variation they explain and how tolerable that percentage is to your goals. But at any rate, our discussion from orthonormal bases notes that because of course u is orthonormal, grabbing any 3 columns of u, especially the first 3 columns of u, is also going to be orthonormal. And so our estimate of gamma, our gamma hat, is just going to be u3 transpose times y. Okay, so what we find is that the way in which we get sort of principal components regressors is simply by taking the singular value decomposition of our centered X matrix, taking the relevant columns from our score, our vector of left singular values, which if we think about it in terms of principal components as our scores, and then if we simply multiply them by y, multiply the transpose of them times y, we actually get the associated coefficients. Okay, so this just goes to show how we can use these nice operations that we get out of least squares in this particular case. So using the singular value decomposition to come up with the orthonormal basis, I think represents, of the 3 most important bases concepts in statistics, certainly I would describe wavelets, Fourier transforms, and principal components bases as the 3. And I think you can see that in this case it fits very nicely into the topic of regression, and it also fits very nicely if we have a large X matrix with a lot of columns that we want to summarize. One caveat I would suggest to be careful of. Again, we get u, we can think of u as these linear combination of our columns of X. If the units of X don't make sense to combine, then this procedure may not make a lot of sense to do. So if the first column of X is a particular kind of units and the second column of X is a different kind of units, then the interpretability of your scores may really suffer as a result. So again, there's a lot of intricacies to do this, and I think if you wanted to learn more about this, a class on multivariate statistics would be the way to go. But I just wanted to reinforce this point that when we have a design matrix that is orthonormal, we work out with a really simple solution for the coefficients. Okay, and next we'll go through a coding example where we go through some of these sorts of examples.